In this video, we are going to discuss about the concept of magnetic field produced by a current carrying conductor. The magnetic field produced by a current carrying conductor is explained by Biot and Savart. Biot and Savart Law. These are the two scientists have explained the concept of magnetic field produced by a current carrying conductor. See, similar to electric field. For example, when charge is at rest, it produces electric field. Electric field at this point is explained by Coulombic inverse square law, Coulomb's law. There, by using Coulomb's law, we have calculated the electric field produced by a stationary charge at rest. Similarly, here the magnetic field produced by a current carrying conductor is explained by Biot and Savart law. So Biot and Savart's law we will study now. See carefully. Here I am going to take some conductor. It can be taken straight or maybe whatever may be the shape, doesn't matter. But whenever you have a conductor is not straight, length of the conductor is not this. Length of the conductor is the straight line joining the two ends of a conductor. This is very important. Effective length we should consider. Effective length is a vector. Okay, this conductor is carrying current I. If it carries current I, if I want to calculate anywhere at certain point magnetic field, here I want a magnetic field. See, the magnetic field direction can be known at this point very easily. That is right hand thumb rule. Current direction represented by the thumb, curling fingers indicates the magnetic field. That means here magnetic field is into the board. Okay, if I say it is B, it is the magnetic field due to entire length of the conductor. Entire length of the conductor. But Biot and Savart explained magnetic field at any point due to small elemental portion. Small portion of the conductor I should take. For example, if I take a small elemental portion of the conductor, say DL, okay, somewhere here, okay, see, current is passing in this direction. DL direction is always taken in the direction of current. So I into DL is called current element. Current element is taken in this direction. Current element is in this direction. Then the magnetic field due to this small portion of the conductor here can be represented with dB. Small portion, small magnetic field. This small magnetic field at this point is into the board. It's okay. But it is an empirical relation. The magnetic field at this point is directly proportional to strength of the current in the conductor. Current increases, magnetic field here increases. Current decreases, magnetic field here decreases. Similarly, the dB is directly proportional to dl. If the length of the element increases, magnetic field here increases. Length of the element decreases, magnetic field decreases. So now we are going to join the elemental portion with a point. This distance can be represented as r. Okay, and this position vector is going to make certain angle with this elemental portion. That angle is say theta. So the magnetic field at this point is directly proportional to sine of the angle. Angle increases, sin theta increases, magnetic field increases. Sin theta is increasing function. And the magnetic field at this point is inversely proportional to square of the distance. Is proportional to 1 by r square. Or dB is inversely proportional to r square. If we combine all these things, this dB is directly proportional to IDL sin theta divided by r square. The proportionality constant is going to replace with mu naught by 4 pi I dl sin theta divided by r square. This is called Biot and Savart law. Biot and Savart law is going to determine the magnetic field due to small elemental portion. If you want a total magnetic field, you should do integration, summation we should do. This is one element, this is another element, this is another element, all you have to add. So that means to get a total magnetic field at this point due to this entire length of the conductor, I should integrate from 0 to L. 0 to L we have to integrate. Okay. So this Biot and Savart law, magnetic field is a vector. So vector form of Biot and Savart law will write. See here carefully. dB bar, I am going to write mu naught by 4 pi is a proportionality constant. The value of mu naught by 4 pi is 10 to the power of minus 7. Okay, mu naught is permeability of free space or permeability of air or vacuum. See, if you want to write a unit for this, you have to send everything this side. Okay, for magnetic field it is Tesla. 4 pi there is no unit. R square is meter square divided by current comes to denominator ampere, dl comes to denominator meter, sine do not have any unit, so m cancel. So Tesla meter per ampere is SI unit of mu naught by 4 pi. Okay, see here how to write a vector form. Understand this very carefully. Mu naught by 4 pi we have written as it is. Current is a scalar, we know from the current electricity concept, I. But dl is a vector, we know. Length of the conductor is a vector. Effective length we should take, that is a vector. So now here we are going to take this position vector r bar divided by r cube. If you rewrite this dl bar cross r bar can be written as dl into r into sine theta divided by r cube. Obviously it becomes dl sine theta by r square. dl sine theta by r square. So that's why this is the vector form of Biot and Savart law. See, vector product I said very clearly, it does not obey commutative law. We should do cross product should be in proper. dl bar cross r bar only we should do. I into dl is called current element vector. Okay, see ma here carefully. Whether this is correct or wrong, we'll check it. At this particular point, current is in this direction, so magnetic field is into the board. Magnetic field is into the board. See here, cross product also we'll do with the help of right hand thumb rule. This is even can be called as right hand screw rule. Here, the I into dl is in this direction. I into dl, elemental vector, I into dl is in this direction. Position vector is this. So that's why L bar cross R bar, dl bar cross R bar can be done like this. Then magnetic field is into the board. Resultant of these two vectors is dB. This dB is perpendicular to dl. dB is even perpendicular to R. This is, remember, always cross product of vectors. Resultant will be perpendicular to both vectors. A bar cross B bar is equal to C bar. Angle between C bar and A bar is 90. C bar and B bar also 90. Why? Because this is perpendicular to plane containing dl and R. dl and R are on the board, so magnetic field either is into the board or out of the board. If we do dl bar cross R bar, magnetic field is into, according to right hand thumb rule also we got here field is into. So that's why dl bar cross R bar only right. If we do R bar cross dl bar, magnetic field is outward, which is wrong here. So this is the right way of expressing vector form of Biot and Savart law. See now, by using this Biot and Savart law, we are going to derive magnetic field at any point due to finite length straight conductor. Magnetic field at any point any point due to straight current carrying conductor. Straight current carrying conductor. Straight conductor means straight current carrying conductor means it is a finite length. That means I know where it begins, where it ends. This is one straight conductor. This straight conductor is carrying current in this direction. Then magnetic field will be into the board. This side it will go into and it will come out. This side outside. Now I would like to calculate magnetic field at this particular point. See, this derivation is not there for board examination. Derivation no need to learn. Final end result is very important for competitive examination. You remember formula. But I am explaining the derivation. Usually in Biot-Savart Law, when we select a point, we should draw a normal onto a conductor. We should draw a normal, perpendicular distance. This is say R. After that, we need to join the ends of the conductor. We need to join the ends of the conductor, which makes an angle alpha. And you have to join the other end of the conductor. That angle is a beta. This angle is a beta. Okay. The magnetic field due to this entire conductor at this point is no doubt it is into the board. Direction is only into. So magnetic field is into the board. That I can directly write expression mu naught by 4 pi I by this perpendicular distance R into sin alpha plus sin beta. This is the mathematical expression for magnetic field at any point due to finite length straight conductor. This we are going to derive in this video. See, observe very carefully. We know only Biot-Savart Law, so we should derive magnetic field at this point due to this conductor by using Biot-Savart Law only. Here some crucial things are there, just understand very carefully. Biot-Savart Law explains only for elemental portion of the conductor. That elemental portion is L, which is at a distance from this point to here. Length is L. Ear to ear length of the conductor is L. I have taken one small portion here, DL. This DL we have to join with this point because in Biot-Savart Law we have done the same. If it is carrying current I, if we take elemental portion, first join these two. This distance we have represented R. This position vector and ideal elemental current or current element makes an angle theta. Okay, then the magnetic field is dB is equal to mu naught by 4 pi ideal sin theta divided by R square. This is Biot-Savart Law. This I am going to apply here for this elemental portion. So that's why I need to join this elemental portion and point B. The distance here already I have taken distance is R. So this I would like to take it as X. I'll take that as X. Okay. Actually this X and this elemental portion are going to make an angle theta. This I should take theta. But what I am doing for my convenience purpose, I am not going to take angle theta here. I'll take angle theta here. See carefully, this is very important. See, when this elemental portion is here, X and R are same, this angle is 0. If I take elemental portion here, angle increases. If I take here, angle increases. If I take here, automatically this theta becomes beta. That means this angle is going to represent this conductor. This angle is going to represent this portion of the conductor. So that's why this angle is going to represent this portion of the conductor. So that's why this angle I have taken as theta, but here this theta is the angle between DL and R only. So that's why here R is X, DL is DL. This angle is now theta actually, but already taken theta here. Here 90 degrees is there, so that's why it becomes 90 minus theta. If I take theta here, it will become 90 minus theta, but I don't want to have some confusion here. So that's why first I have taken here theta. This is 90 minus theta. So then magnetic field at this particular point due to this elemental conductor can be written as dB is equal to mu naught by 4 pi. Current passing through this elemental portion is I. Length of the elemental portion is dl into sine of this angle only we should take there. So that's why it is 90 minus theta divided by x square. Divided by x square. Exact duplication of Biot-Savart law. Okay, now I have to integrate this to get total magnetic field at this point. Okay, so before that dB is equal to mu naught by 4 pi I dl sine 90 minus theta is cos theta divided by x square. Here I have to do the integration. Integration, what I am doing, from here I have to integrate alpha to get this length. To get this length I have to integrate beta. This is in one direction, this is in another direction. So that's why one angle I will take it as positive, another angle I will take it as negative. Below the x-axis I will take it as a negative angle, above this axis is taken as positive angle. So I have to integrate this one from minus beta to alpha. Anyway, this total angle I have to integrate. That's what we have taken there. Important. See here, functions are in different form. Integral of dB is b. Integral of dB is b. You know this. Now, what I am doing, some geometry I am using here. See, this is one right angle triangle. By using this right angle triangle, I can calculate cos theta. Cos theta is adjacent side by hypotenuse. For this right angle triangle, this is theta, this is adjacent, this is opposite, this is hypotenuse. So cos theta is r by x. R by x. Cos theta is r by x. Similarly, I am going to use another trigonometric function, that is tan theta. Tan theta is opposite side by adjacent side. That is L by R. That is L by R. Okay, from this I can write L is equal to R into tan theta. Now I want DL value, so that's why I am differentiating this. Differentiation of L is DL. R is constant, so I left it as it is. Differentiation of tan theta is secant square theta. But again I should apply theta differentiation, that is d theta. Because here I don't know with respect to what function I am differentiating. So I have replaced it like this. Is that okay? So now what we are going to do, here we are going to substitute minus beta to alpha mu naught by 4 pi I into dl can be written as r secant square theta, r secant square theta d theta into cos theta is there. That cos theta I am continuing as it is, divided by x square is there. I need to know the value of x. Already here the value of x can be written as x is equal to, here x can be written as r by cos theta. So that's why x value is now, it is going to represented as r square by cos square theta. So cos square theta goes to numerator, 1r gets cancels out, and now I am going to take constants outside. Magnetic field B is equal to mu naught by 4 pi is proportionality constant. Current passing through the conductor is remains the same, and here you see cos square theta goes here. secant square and cos square are reciprocal. Okay, so that's why when it goes there, cos square theta can be written as 1 by secant square theta. Those two gets cancels out. And what we left over here, we have one more r also taken outside. Now integral of minus beta to alpha, what is left inside? Only cos theta into d theta is left. Integral of cos theta is sin theta. So that's why magnetic field B is equal to mu naught by 4 pi I by r into integral of cos theta is sin theta. For this we have to apply limits from minus beta to alpha. First we have to substitute upper limit. So magnetic field B is equal to mu naught by 4 pi I by r into sin alpha upper limit minus lower limit minus sin of lower limit is minus beta. So sin of minus theta is minus sin theta. So that's why magnetic field B can be written as mu naught by 4 pi I by r into sin alpha plus sin beta. Minus into minus plus. So this is the expression for magnetic field at any point due to straight finite length conductor. So B is equal to mu naught by 4 pi I by r into sin alpha plus sin beta. By using this expression, we can solve infinite number of problems with ease. Only thing you have to remember is, we have taken one straight conductor, we have selected a point, we have drawn normal onto a conductor, that perpendicular distance is r. Afterwards we join the ends of the conductor, this angle is alpha, this angle is beta. Then magnetic field at this point due to this straight conductor is B is equal to mu naught by 4 pi I by r into sin alpha plus sin beta. By using this, we are going to do some more applications. See carefully this. See now, magnetic field at any point due to straight current carrying conductor is mu naught by 4 pi I by r into sin alpha plus sin beta. This formula is heart. You remember this. For example, if I want to calculate magnetic field at any point due to long conductor even can be called as infinite length conductor. It means this end I don't know, this end also I don't know, such kind of conductor. If it carries current downward, for example, if it is downward, magnetic field here is into, here is out. So now I would like to calculate magnetic field at this particular point, say B. Here I want magnetic field. Okay, first what I should do, I should draw a normal onto a conductor. This distance is going to represent with the letter R. It is not radius, it is perpendicular distance. Remember this. Next rule is to join the ends of the conductor. How can I join, you tell me? This end I don't know, this end also I don't know. Then how can we join? Difficult. But in mathematics, we have one statement, two parallel lines meets at infinity. That means to join these ends, I have to draw a parallel line. These parallel lines are going to meet at this infinity as well as this infinity. That means this angle now becomes alpha. This alpha is 90 degrees. This angle becomes beta. This angle is also 90 degrees. So, if you substitute these things in this equation, you will get B is equal to mu naught by 4 pi I by r into sin 90 plus sin 90. That is, sin 90 is 1, sin 90 is 1, 1 plus 1, 2. So magnetic field at any point due to infinitely long conductor is mu naught by 4 pi 2I by r. 2I by r. That's all. In a very simple way we can determine. Next application we'll see. For example, see here carefully. One end of the conductor is, I know, it begins here. I don't know where it ends. This I can call it as a semi-infinite conductor or semi-long conductor, because one end is known, other end we don't know. If at all, if it carries current in this direction, then here magnetic field is into. If I want to calculate magnetic field at this point, see, conveniently I am selecting. I have selected here. Then I have to draw a normal onto a conductor. Yes, exactly. It touches the tip of the conductor. This distance is say r. I need to join the ends. One end is fortunately joined. Angle is 0. Beta is 0. Okay, other end I have to join. So I have to draw a parallel line. So that's why alpha value becomes 90 degrees. Okay, then simple substitution. Magnetic field B is equal to, magnetic field at this point B is equal to, this is beta, this is B, don't confuse. B is equal to mu naught by 4 pi I by R into sine 90 plus sine 0. Sine 0 is 0, sine 90 is 1. So magnetic field B can be written as mu naught by 4 pi I by R into 1. This is 1. So mu naught by 4 pi I by R is the answer. So why you conveniently selected point here? If I select point here, for example, if I have selected point here, then what will happen? Nothing. It's a simple, draw a normal onto a conductor R. You have to join this end, join them with a parallel line. So alpha becomes 90. Okay, this end will join like this. This angle is a beta. Then magnetic field here B is equal to mu naught by 4 pi I by R into sine 90 plus sine beta. This angle, if the geometry is known, we can calculate. Geometry we don't know, we'll represent like this. Then magnetic field B is equal to mu naught by 4 pi I by R into sine 90 is 1 plus sine beta. We will measure like this. So if at all, if I may consider point neither here nor here, I may consider point here. If I consider point here, if I draw a normal onto a conductor, there is no conductor here. So that's why what I do, I'll imagine conductor here. I'll take one conductor here. This is very important. See, this is insufficient length conductor. Here I want to calculate magnetic field. So when I draw a normal onto a conductor, then there is no conductor here. So I have joined here. This conductor I have imagined here. Now what will happen? Beta value becomes 0. Alpha value becomes infinite 90 degrees. Okay, if at all, if it is not a infinite conductor, if it is a finite conductor, then what will happen? We'll join this. You will get alpha. Okay, then magnetic field due to this entire conductor. From here to here I am calculating. That I will write it as B1. That is mu naught by 4 pi I by R into sine alpha. That's it. Because sine 0, 0. So this is due to entire conductor. But what asked in the problem, we need to calculate magnetic field from here to here only. This is additional conductor we have imagined. So I will calculate magnetic field due to this conductor. For this conductor also, beta value is 0, but alpha value is different. This angle, I can represent it as, for example, say phi. If I represent it as phi, then this is magnetic field due to only this portion of the conductor. That is mu naught by 4 pi I by R into sine phi. See, here to here magnetic field is B1. Here to here magnetic field is B2. I want to calculate from here to here. That means net magnetic field due to this conductor can be written as B1 minus B2. This is additional conductor I have taken. Magnetic field produced by this conductor is involved here. This I have calculated here. I am subtracting from this from this, then I will get B. This conductor I will get it. So that's why B is equal to B1 value. Everything here you take common, mu naught by 4 pi I by r, mu naught by 4 pi I by r is common, mu naught by 4 pi I by r is common. Then you will get sin alpha minus sin phi. This is going to the magnetic field due to insufficient length current carrying conductor. That means we are going to calculate every point, everywhere point except this will do it in the next application. See here, whenever we have a current carrying conductor, I am able to calculate magnetic field here. Because it is insufficient, I will extend, I will calculate. If I take here, I can calculate directly. Alpha becomes 0, beta value I have to measure. If I take here, alpha is there, beta is there, I can calculate. Everywhere, anywhere you take point, I can calculate. Anywhere in front of the conductor. But now we are going to try to calculate a magnetic field at a point along the axis of the conductor. Along the axis of a current carrying conductor. Here you see, drawing normal is not possible. And if you join this end, angle becomes 0. If you join this end, angle also becomes 0. Alpha 0, beta 0, 0 plus 0, 0, 0 into anything 0. So magnetic field at any point along the axis of a current carrying conductor, magnetic field is 0. Okay, we will see the next application. See, a current carrying conductor carries current I of length 3L is bent in the form of an equilateral triangle. Then, for example, current is passing like this. In clockwise direction. I need to calculate magnetic field at the centroid. Of an equilateral triangle. Centroid is the point of intersection of the medians. If L is the side of an equilateral triangle, because it is 3L, it is bent in the form of L, 3L, equilateral triangle. Okay, so I need to find the median length. Here to here it is median, it divides two equal parts, L by 2, L by 2. So length of this median, this is hypotenuse. One is opposite side, another one is adjacent side. If I take it is x, this is L square is equal to x square plus L square by 4. X square is L square minus L square by 4. X value is root over 3L square by 4. Is this simplification is clear? So the value of x is root 3L by 2. That means this length of the median, x value is root 3L by 2. But the median, this centroid divides in the ratio 2:1. It divides in the ratio 2:1. This two portions of the length is how much means? Total this median is divided into 3 parts. Here 2 parts, here 1 part. Total is 3 parts. 2 part is how much means? 2 by 3 into this root 3L by 2. Root 3 cancels this root 3 times 2 cancel. So it is L by root 3. This distance, this portion of the distance is L by root 3. Okay, this one portion is how much means? 1 by 3 root 3L by 2. This 3 cancels, root 3 cancels 3 by root 3 times. So answer is L by 2 root 3. So this is L by 2 root 3. These things you have to, very very important, you should remember. Okay, now we know this length is L by root 3, this length is L by 2 root 3. That means this length is L by 2 root 3. L by 2 root 3. This length is L by 2 root 3. This length is L by 2 root 3. See, when a conductor is carrying current in a equilateral shape, if this conductor produces magnetic field, here is into. This one is also into. This one is also into. That means at the centroid, magnetic field is B1 plus B2 plus B3 is equal to B. B1, B2, B3 are equal. We'll see first. According to Biot-Savart Law, when you have a finite length conductor, if you select a point, you should draw a normal onto a conductor. That is R. R value is L by 2 root 3. Okay, join the ends. Already joined. This angle is alpha. This angle is beta. See here, this angle is, total angle is 60. This is 30. This is 90. So this is 60. Alpha value is 60. Beta value is 60. Okay. Similarly everywhere. This is L by 2 root 3. This angle is 60, 60. Again L by 2 root 3, 60, 60. So B1 is equal to B2 is equal to B3. So net magnetic field is 3 times B1. B is equal to 3 times B1. Magnetic field due to straight conductor is mu naught by 4 pi I by R into sin alpha plus sin beta. So I will calculate B1 here. B1 is mu naught by 4 pi I by R into alpha is 60. Sin 60 is root 3 by 2 plus sin 60 is again root 3 by 2. So that is B1 is equal to mu naught by 4 pi I by R into 2 root 3 by 2. 2 cancel. So the value of B1 is root 3 times mu naught by 4 pi I by R. I by R. Okay. Now the value of R I should substitute. So B1 is equal to root 3 into mu naught by 4 pi I by R is a perpendicular distance which is L by 2 root 3. So if it goes to numerator, the value of B1 is root 3 into root 3 is 3. 3 2s are 6. 6 times mu naught by 4 pi I by L. So B1 value is mu naught by 4 pi 6 times I by L. 6 3s are 18. So magnetic field due to a current carrying equilateral triangular loop is 18 times mu naught by 4 pi I by L. See, this is formula, you can remember it as a synapses. But when you remember this as a synapses, you should focus on this part where L is side of an equilateral triangle. In the examination, maybe the examiner may ask this question smartly. They'll take L length of the conductor carrying current I. It is bent in the form of an equilateral triangle. Then side becomes L by 3. Side becomes L by 3. That means B is equal to 18 into mu naught by 4 pi I by side of the equilateral triangle. You should substitute. The side is L by 3. So this is L by 3. Then 18 3s. So this is 18 into 3 mu naught by 4 pi I by L. Okay. 18 3s are 54. So it becomes 54 times mu naught by 4 pi I by L. Remember, this is important. It is not 18 times, it is 54 times. So here L is side of the equilateral triangle. Whatever the side you will get after bending this wire in the form of an equilateral triangle, that is supposed to substitute here. This is very important, remember. Next application, A conductor carrying current I, its length is 4L. It is bent in the form of a square. If it is bent in the form of a square, each side of the square is L. If it carries current like this, then we need to calculate magnetic field at the center. This conductor produces into field, this also produces into, this also produces into, this also produces into. Center is a symmetry. So magnetic field at the center can be written as 4 times B1. Calculate one conductor, multiply with 4. Okay, what is the rule for calculating magnetic field at any point? Rule is draw a normal onto a conductor. This becomes R. This R value is here L by 2 because center is equidistance. Afterwards we have to join the ends. See here, total angle is 90. This is 45. So this angle is 45. This angle also 45. That means alpha 45, beta 45. So magnetic field B is equal to 4 times. Magnetic field due to one straight current carrying conductor, formula is mu naught by 4 pi I by R. R is L by 2. Into sin 45 plus sin 45. 2 times sin 45. Sin 45 is 1 by root 2. So that's why root 2 cancels this one root 2 times. This 2 goes to numerator. So magnetic field becomes 4 2s are 8 and root 2. 8 root 2 mu naught by 4 pi I by L. Again, if you want to remember it as a formula, L is length of the side. In the examination, if they ask a conductor is carrying current I, length of the conductor is L, it is bent in the form of a square, then side becomes L by 4. So if it is L by 4, I will substitute here L by 4. So magnetic field B is equal to 8 root 2 mu naught by 4 pi I by L by 4. 4 goes to numerator, it becomes 32. 32 root 2 mu naught by 4 pi I by L. So this is how you have to use this formula. Be careful. Where L is side of the square. Similarly, maybe it is bent in the form of an hexagon. At the center means all the diagonals will meet at the center. Here if you want to calculate, you do your own derivation. Magnetic field B is equal to 6 times B1. If you do it, B will get 4 root 3 mu naught by 4 pi I by L, where L is side of the hexagon. If 6L is bent, it is L. If it is 3L is bent, it is L by 2. If it is 2L is bent, you calculate and substitute. That's how we have to calculate. This is how we are going to calculate magnetic field at any point due to straight conductors. Okay? If you like this concept, you please subscribe my channel Sharatneet Academy, and you can share these links to your friends, and you please subscribe and press the bell icon so that you will get notification quickly. Whenever we upload video, you will get the notification. You can follow these classes, okay, to improve your physics. Thank you.